An important law in the field of diffusion, we are discussing the topic of diffusion. So, Fick's first law of diffusion. In the last video, we just had an introduction of diffusion. In particular, we saw two examples, one of carburization of gear and another production of NP junction in electronic circuit, which are based on diffusion. These diffusion processes are governed by two important laws, both derived by Fick, and they are called Fick's first law of diffusion and Fick's second law of diffusion. We will first begin with the first law. What is this Fick's first law of diffusion? So, this law can be understood in with comparison with other corresponding laws which we have for heat flow. So, let us have a comparison of heat flow, then charge flow, and mass flow. So, let us look at the flux. So, what is the flux in heat flow? The flux in heat flow is the heat flux. So many heat flux, let us call that Q, and the unit is so many joules crossing per unit area per second. So, that is the flux in heat flow. Now, it is known that heat flows due to a existence of a particular gradient. So, what is the gradient of heat flow? What is the gradient which gives us heat flux? So, that gradient we know is temperature gradient. Temperature gradient, let us call that dT by dx. So, if there is a uniform temperature in a body, there will be no heat flux. So, only when there is a gradient where the temperature is changing with position, we have a heat flux. We then have a law connecting the flux to the temperature gradient. In the heat flow case, it is the famous Fourier's law of heat conduction. And that law relates the heat flux to the temperature gradient through a simple expression, Q is equal to minus kappa dt by dx. So, essentially it is saying that the heat flux is proportional to the temperature gradient, and the proportionality constant kappa is our material property. So, material property is thermal conductivity kappa, which has the units watts per meter per Kelvin. And finally, for our historical record, let us write down the year in which it was discovered, and that is this is a very old law, more than 200 years now, 1807. Now, so more than 210 years ago, Fourier established how the heat flux is related to the temperature gradient, and that law we know as Fourier's law of heat conduction. Then came the study of charge flow or the electric current. So, here the flux is charge flux, also known as current density, so this is given a symbol J, units will be ampere per meter square, which is same as actually coulombs per meter square per second. So, you can compare it joules per meter square per second, here it is coulombs per meter square per second. So, now the charge is flowing. So, what is the driving force or what is the driving gradient for this charge flow? So, you know charge will flow only if there is a potential gradient, electric potential gradient. Electric potential gradient dV by dx, and the law connecting them is the well known Ohm's law, which we can write as J is equal to minus sigma dV by dx. So, the material property involved here is the electrical conductivity, sigma, and the unit is Siemens per meter, or you can call it ohm inverse meter inverse. And this law was discovered 20 years later in 1827, and in fact, the motivation for this law or the inspiration for this law for Ohm came from the study of Fourier's law of heat conduction. Since he saw that in heat conduction there is a flux of heat which is proportional to the temperature gradient, he asked what should be the flux and the gradient, corresponding gradient in the case of charge flow. So, he could relate these two in 1827, 20 years after Fourier's law of heat conduction. Now, we come to our interest, that is the mass flow. So, here the flux is mass flux, which we also call J. So, now this is mass per unit area per unit second, per second. So, kg per meter square per second, or sometimes mass can also be written in the units of mole. So, you can have mole per meter square per second. So, that is mass flux. Now, it was Fick who derived this law, and Fick again was inspired by heat flow and charge flow. He asked the question that what is the driving force for mass flux, and he found that it should be the charge gradient, it should be the concentration gradient. So, the corresponding gradient is the concentration gradient. Let us write it as dC by dx. And Fick, just by analogy, so this is a demonstration of power of analogy and success of analogy in science. So, just by analogy he could write, so Fick's first law, that the mass flux should be nothing but proportional to the concentration gradient. The proportionality constant he called d. So, d dC by dx. So, the property d here was named diffusivity, or diffusion, sometimes also known as diffusion coefficient. The units of this is meter square per second, and this one was in 1855. So, you can see another 28 years passed before Fick could establish his famous first law, that the mass flux is proportional to the concentration gradient. So, this will be an important law for us in the study of diffusion. And remember that since this is, if you see the unit of diffusivity meter square per second, this indicates that C for our C should always be in the units of per unit volume. So, it should be either kg per meter cube, the concentration should be volumetric concentration, kg per meter cube or moles per meter cube. We saw in the phase diagram we used atomic percent or mole percent or weight percent as our x axis of the phase diagram, and that was also the units of concentration. That unit is fine, but if we want to use Fick's first law, there we should use the concentration in per unit volume, then only we will get a consistent D, which will be in meter square per second. So, let us look at a little bit more about this Fick's first law. So, J is equal to minus D del C by del x. J is mass flux. So, essentially by flux you mean, so let us have an area. Across this area there is a concentration gradient. So, let us say that there is a concentration which is changing, and then we are looking. So, if there is a high concentration on this side and a low concentration on this side, so mass will cross this area in this direction from high concentration to the low concentration. So, mass flows from high concentration to low concentration regions. So, you can see from here that if mass is flowing to the right, this is our x axis. So, the flux is in the positive x direction, this is what we will call a positive flux. But to have the positive flux, so means if J is positive, then del C by del x, the concentration gradient, we have a higher concentration on the left hand side and a lower concentration on the right hand side. So, this gradient del C by del x is negative. So, this is negative. And since we want to associate the proportionality constant with the material property, and it will not be nice to have a negative sign with a material property. So, by convention that is the reason why we have put a negative sign. In fact, that is the reason why. So, this negative sign has no any fundamental derivation or anything, this is just a desire by the scientific community to keep their conductivity, the thermal conductivity, the electrical conductivity, and now the mass diffusivity as positive quantities. If we want to keep them as positive quantity, we have to have minus sign in all these equations. So, that is the reason for this minus sign. So, this D, if we want positive, then this minus sign should be there to make D positive. So, D is diffusivity, or diffusion coefficient. I have already written the units for diffusion coefficient. You can see the consistency of that the dimension of D will be the dimension of J divided by the dimension of the concentration gradient and if we write it in terms of units. So, we said that J is kg per meter square per second, and concentration gradient, I insisted that if you want D to be meter square per second, concentration should be the volumetric concentration. So, in this case it should be kg per meter cube, but since it is a gradient, one more meter in the denominator comes. So, if you work this out, it will be simply meter square per second. So, you want D to be meter square per second. So, we insist concentration to be in kg per meter cube. Of course, kg is not required, I means not essential, it can be moles per meter cube, but then the flux should also be in moles per meter square. So, the flux, the unit of mass in flux and the unit of mass in the concentration should be consistent. So, if this is mole, this also should be mole, if this is gram, that should also be in gram, and so on. So, this is the mathematical form, and essentially actually Fick did not derive it, and there is no such derivation for this first law, but we should be, we will see later in this course that we will be able to derive this law from the first principle in by atomic movement, but at the moment we will not do that, we will just take this law as given. So, and this will be our flux to concentration gradient relation, and this is our Fick's first law. It is interesting to note that Fick was actually a physiologist. He was not an engineer interested in carburization or not, or neither in doping of semiconductors. He was interested in the diffusion of oxygen in blood, and that was the reason why he was interested in diffusion problems, and he came up with this nice relationship. One more point about diffusivity let us talk about. So, this diffusivity D is temperature dependent. So, it is highly temperature dependent, and it follows an exponential law. D is equal to D naught exponential minus Q by R T. So, since D naught is a constant which comes before the exponential, it is known as pre-exponential factor. R is the well known gas constant, and T, like in all thermodynamic equations, it is absolute temperature. And Q is a constant which is known as the activation energy. Activation energy. So, in fact, so this again we will see that when we will try to derive Fick's first law from the first principles of atomic jumps, then in the process we will also derive this temperature dependence of diffusivity, but at the moment we are taking it purely as empirical relation. So, we can call it for the moment an empirical relation that is based on experiments. Empirical relation, but we can note to be established later by atomic mechanism of diffusive jumps. Also, we can see that this empirical relation can actually be established by experiments. So, if we have experimental data, let us say of as a temperature, if we do an experiment, diffusion experiment on different temperature, and if we measure the diffusivity. So, if we have at temperature T diffusivity D1 and temperature T2 diffusivity D2 and so on. So, if we have a table like this, then it is possible to get the pre-exponential factor and Q, or it is possible to verify whether this relationship is true or not by plotting. You can see we will get a straight line if we simply take log of this equation. So, if we take the log, then we will have log D is equal to log d naught minus q by r 1 by t. So, you can see that if I plot log d as my y axis and 1 by t as my x axis, then I should get a straight line. So, let us do that. So, if x axis is 1 by t and the y axis is log d in my plot, and if I plot this data of diffusivity versus temperature, so then these data should actually give me a straight line. So, since it is an experimental data, all of them may not be exactly on a line, but it should follow a line. So, I should draw a best fit line to get this relationship. So, you can see now that the intercept of this line will give you that is, if 1 by t is 0, then that is log d naught. So, log d naught can be found from intercept, and the slope of this line should be nothing but minus q by r. So, since r is a constant, gas constant, you can find the activation energy q from an experiment like this. So, in fact, experiments like this is what means, if you have a temperature diffusivity data and if you are able to fit a straight line to log d versus 1 by t, that gives you the reason to believe that d should have an exponential relation like this, and that is why we will call this an empirical relation. But later on, when we talk about atomic mechanism of diffusion, we will see that this comes out from an atomic model of diffusion also.